NCERT Chemistry Class 12 P Block Elements 7.23 Group 18 Elements. Group 18 consists of elements helium, neon, argon, krypton, xenon, radon and oganesson. All these are gases and chemically unreactive. They form very few compounds. Because of this, they are termed as noble gases. Occurrence. All these gases except radon and oganesson occur in the atmosphere. Their atmospheric abundance in dry air is about 1% by volume, of which argon is the major constituent. Helium and sometimes neon are found in minerals of radioactive origin, example pitchblende, monazite, clevite. The main commercial source of helium is natural gas. Xenon and radon are the rarest of elements of the group. Radon is obtained as a decay product of radium-226. Oganesson has been synthetically produced by collision of californium atoms and calcium ions. Oganesson has its symbol Og, atomic number 118, atomic mass 294 and electronic configuration Rn5f14 6d10 7s2 7p6. Only very small amount of oganesson has been produced. Its half-life is 0.7 milliseconds. Therefore, many predictions about its chemistry have been made. Here, except for oganesson, important atomic and physical properties of other elements of group 18 along with their electronic configuration are given in table 7.12. The trends in some of the atomic, physical and chemical properties of the group are discussed here. Electronic configuration. All noble gases have general electronic configuration ns2np6 except helium, which has 1s2. Many of the properties of noble gases, including their inactive nature, are ascribed to their closed shell structures. Due to stable electronic configuration, these gases exhibit very high ionization enthalpy. However, it decreases down the group with increase in atomic size. Atomic radii increase down the group with increase in atomic number. Electron gain enthalpy. Since noble gases have stable electronic configurations, they have no tendency to accept the electron and therefore have large positive values of electron gain enthalpy. Physical properties. All the noble gases are monoatomic. They are colorless, odorless and tasteless. They are sparingly soluble in water. They have very low melting and boiling points because the only type of interatomic interaction in these elements is weak dispersion forces. Helium has the lowest boiling point, 4.2 Kelvin, of any known substance. It has an unusual property of diffusing through most commonly used laboratory materials such as rubber, glass or plastics. Chemical properties. In general, noble gases are least reactive. Their inertness to chemical reactivity is attributed to the following reasons. 1. The noble gases except helium have completely filled ns2np6 electronic configuration in their valence shell. They have high ionization enthalpy and more positive electron gain enthalpy. The reactivity of noble gases have been investigated occasionally ever since their discovery, but all attempts to force them to react to form the compounds were unsuccessful for quite a few years. In March 1962, Neil Bartlett, then at the University of British Columbia, observed the reaction of a noble gas. First, he prepared a red compound which is formulated as O2 plus PtF6 minus. He then realized that the first ionization enthalpy of molecular oxygen was almost identical with that of xenon. He made efforts to prepare same type of compound with xenon and was successful in preparing another red color compound Xc plus PtF6 minus by mixing PtF6 and xenon. After this discovery, a number of xenon compounds, mainly with most electronegative elements like fluorine and oxygen, have been synthesized. The compounds of krypton are fewer. Only the difluoride has been studied in detail. Compounds of radon have not been isolated but only identified RnF2 by radio tracer technique. No true compounds of argon, neon or helium are yet known. A. Xenon fluorine compounds. Xenon forms three binary fluorides XeF2, XeF4 and XeF6 by the direct reaction of elements under appropriate experimental conditions. XeF6 can also be prepared by the interaction of XeF4 and O2F2 at 143 Kelvin. XeF2, XeF4 and XeF6 are colorless crystalline solids and sublime readily at 298 Kelvin. They are powerful fluorinating agents. They are readily hydrolyzed even by traces of water. For example, XeF2 is hydrolyzed to give xenon, HF and O2. The structures of the three xenon fluorides can be deduced from VSPR and these are shown in figure 7.9. XeF2 and XeF4 have linear and square planar structures respectively. XeF6 has 7 electron pairs, 6 bonding pairs and 1 lone pair and would thus have a distorted octahedral structure as found experimentally in the gas phase. Xenon fluorides react with fluoride ion acceptors to form cationic species and fluoride ion donors to form fluoroanions. B. Xenon-oxygen compounds. Hydrolysis of XeF4 and XeF6 with water gives XeO3. Partial hydrolysis of XeF6 gives oxyfluorides XeF4 and XeO2F2. XeO3 is a colorless explosive solid and has a pyramidal molecular structure. XeOF4 is a colorless volatile liquid and has a square pyramidal molecular structure. Uses. Helium is a non-inflammable and light gas, hence it is used in filling balloons for meteorological observations. It is also used in gas-cooled nuclear reactors. Liquid helium boiling point 4.2 Kelvin finds use as cryogenic agent for carrying out various experiments at low temperatures. It is used to produce and sustain powerful superconducting magnets which form an essential part of modern NMR spectrometers and magnetic resonance imaging MRI systems for clinical diagnosis. It is used as a diluent for oxygen in modern diving apparatus because of its very low solubility in blood. Neon is used in discharge tubes and fluorescent bulbs for advertisement display purposes. Neon bulbs are used in botanical gardens and in greenhouses. Argon is used mainly to provide an inert atmosphere in high temperature metallurgical processes, arc welding of metals or alloys, and for filling electric bulbs. It is also used in the laboratory for handling substances that are air sensitive. There are no significant uses of xenon and krypton. They are used in light bulbs designed for special purposes. Summary. Group 13 to 18 of the periodic table consists of p block elements with their valence shell electronic configuration ns2 np1 to 6. Groups 13 and 14 were dealt with in class 11. In this unit, remaining groups of the p block have been discussed. Group 15 consists of 5 elements, namely nitrogen, phosphorus, arsenic, Sb and bismuth, which have general electronic configuration ns2np3. Nitrogen differs from other elements of this group due to a small size, formation of p-pi multiple bonds with itself and with a high electronegative atom like oxygen or carbon, and non-availability of d orbitals to expand its valence shell. Elements of group 15 show gradation in properties. They react with oxygen, hydrogen and halogens. They exhibit two important oxidation states, +3 and +5, but +3 oxidation is favored by heavier elements due to inert pair effect. Dinitrogen can be prepared in laboratory as well as on industrial scale. It forms oxides in various oxidation states as N2O, NO, N2O3, NO2, N2O4 and N2O5. These oxides have resonating structures and have multiple bonds. Ammonia can be prepared on large scale by Haber's process. HNO3 is an important industrial chemical. It is a strong monobasic acid and is a powerful oxidizing agent. Metals and non-metals react with HNO3 under different conditions to give NO or NO2. Phosphorus exists as P4 in elemental form. It exists in several allotropic forms. It forms hydride PH3, which is a highly poisonous gas. It forms two types of halides as PX3 and PX5. PCl3 is prepared by the reaction of white phosphorus with dry chlorine, while PCl5 is prepared by the reaction of phosphorus with SO2HCl2. Phosphorus forms a number of oxoacids. Depending upon the number of pOH groups, their basicity varies. The oxoacids which have pH bonds are good reducing agents. The group 16 elements have general electronic configuration ns2np4. They show maximum oxidation state +6. Gradation in physical and chemical properties is observed in the group 16 elements. In laboratory, dioxygen is prepared by heating KCl3 in a presence of MnO2. It forms a number of oxides with metals. Allotropic form of oxygen is O3, which is a highly oxidizing agent. Sulfur forms a number of allotropes. Of these, alpha and beta forms of sulfur are the most important. Sulfur combines with oxygen to give oxides such as SO2 and SO3. SO2 is prepared by the direct union of sulfur with oxygen. SO2 is used in the manufacture of H2SO4. Sulfur forms a number of oxoacids. Amongst them, the most important is H2SO4. It is prepared by contact process. It is a dehydrating and oxidizing agent. It is used in the manufacture of several compounds. Group 617 of the periodic table consists of the following elements: fluorine, chlorine, bromine, iodine, and astatine. These elements are extremely reactive, and as much they are found in the combined state only. The common oxidation state of these elements is -1. However, highest oxidation state can be +7. They show regular gradation in physical and chemical properties. They form oxides, hydrogen halides, interhalogen compounds, and oxoacids. Chlorine is conveniently obtained by the reaction of HCl with KMnO4. HCl is prepared by heating NaCl with concentrated H2SO4. Halogens combine with one another to form interhalogen compounds of the type XX1, where X1 is higher than X. A number of oxoacids of halogens are known. In the structures of these oxoacids, halogen is the central atom which is bonded in each case with one OH bond as XOH. In some cases, X double bond O bonds are also found. Group 18 of the periodic table consists of noble gases. They have ns2np6 valence shell electronic configuration except helium, which has one s2. All the gases except radon occur in the atmosphere. Radon is obtained as a decay product of radium-226. Due to complete octet of outermost shell, they have less tendency to form compounds. The best characterized compounds are those of xenon with fluorine and oxygen only under certain conditions. These gases have several uses. Argon is used to provide inert atmosphere. Helium is used in filling balloons for meteorological observations. Neon is used in discharge tubes and fluorescent bulbs. That's all for today. Please subscribe for more such videos.